In this video, we're going to look at the speed of waves, the energy transported by wave, and some wave reflections. So to begin, we have a wave equation, and in this one-dimensional linear wave equation, we had the speed c over the wave. But to actually find c, you need to do some physics. Now, I'm not going to do that physics for you right now, but I'm going to tell you what the speed of some different sorts of waves are. So for a thin wire, or a string, you can imagine a guitar string, or a slinky, we have some sort of transverse wave motion here. The displacement from equilibrium is given by y as a function of x and t. The one-dimensional linear wave equation for y is given by this equation here, and this term here is sitting where c squared would normally be. In this case, c squared is given by the tension divided by the mass per unit length, and so the speed is a square root of this term here. For sound waves, we have pressure, p, as a function of x and t following a one-dimensional linear wave equation. The wave motion in this case, as you can see, is longitudinal. C squared is given by this term here, and when we look at what those different things are, we have gamma as the ratio of heat capacities at constant pressure and constant volume, which is 1.4, R is the gas constant, M is the molar mass, and T is the temperature. At room temperature 300 Kelvin, we find for air a speed of sound of about 350 meters per second, which is also what we observe. Another kind of wave is the electromagnetic wave. It's a bit more complicated. There are transverse magnetic and electric components. If we look at the one-dimensional linear wave equation for the electric field, E is a function of x and t, we get this wave equation here. C squared is given by 1 divided by mu naught epsilon naught. And plugging these values in, we get the speed to be this, which is in fact the speed of light. The final kind of wave that I'll mention is a water wave. Now it's pretty complicated. The motion of the particles in water I've shown in this animation. On the bottom of the ocean, they're just going backwards and forwards because you can't go through the solid floor. And as you tend towards the surface, the motion of the particles becomes circular. But this collective motion gives rise to a traveling transverse wave on the surface of the ocean. The speed of this transverse wave is given by the square root of g divided by k, multiplied by the hyperbolic tan, that's tanh, of k times h. G is acceleration due to gravity, h is the depth of the water, and k is the wave vector. So that is, for a sinusoidal wave, that's 2 pi divided by lambda. So if we're dealing with a single frequency wave that has a particular wavelength and frequency, then we can write down the speed of the wave. But if we have some sort of mixture of two different waves with different wavelengths, then they'll travel at different speeds. And this is an example of dispersion, and water waves are strongly dispersive. This is in contrast to, say, light in a vacuum, which is not dispersive at all. Light can undergo dispersion if it travels into a medium like glass, where the speed changes as a function of wavelength. Sound waves in air are very weakly dispersive. It's hard to measure any sort of dispersion for sound in air. And transverse waves propagating along a thin wire tend not to be dispersive. Although if the wire becomes stiff, then you can start to see dispersion. The energy transported by wave per second, i.e. the power, so it's proportional to the square of the amplitude. For example, on a string, the power transported is a half. This is the linear density, the square of the angular frequency, and A is the amplitude and C is the speed. So it's proportional to the square of this amplitude here. For sound, now we have power per meter squared, because imagine sound traveling in a great sheet, in sort of a three-dimensional space. This is the power delivered per meter squared of a sound wave. We have half again. This is now the density of the air, or the water, or whatever it is. Again, the angular frequency, the amplitude squared, and the speed of the sound wave. For light, the equation looks very similar again, except now the density is replaced with epsilon naught, E is the electric field, and C is the speed of light. And this is power per meter squared as well. So you can see these three equations for the power look kind of similar. Just because the waves are in different media, the amplitude is different. Here it's a displacement, here it's a displacement, here it's an electric field. The speeds are different because they're different waves, and the constant, in this case, it's a linear density, a bulk density. In this case, it's this constant that comes from electromagnetism. Now what happens when waves change speed? And I'm going to give an example here for waves on a string. So here is some wave, it's just a sort of a wiggly thing, and it's traveling in this direction. I'm going to let this animation loose and let you know that at this point here, the density of the string changes. So imagine tying a thin string to a thick string, or have two guitar strings of different densities or different weights and stick them together and see what happens. So the wave travels along, and when it changes from one medium to another, we get some transmission and some reflection. We see that on this side, the wave has become shorter, so the wavelength is reduced. And on this side, it's the same wavelength that we had originally, and some of the energy is reflected and some of the energy is transmitted. The parameters are used for this animation. So at x equals 40, that's where we have a change of density. The density, in fact, increases by a factor of 4. Now, something you want to maybe notice here is that if we look at where this big peak is, as we hit the wall and look at the reflection, this big peak is now pointing down. So the reflected wave has a phase change of pi. It's 180 degrees. Phase change is upside down, in other words. But the wave that's transmitted has no phase change. What if we go the other way? So we start with a density of 4 and go to a density of 1. So we start off like this, hits the interface. We see now on reflection there is no phase change, so the big peak is still pointing up, and the other side, the big peak is also pointing up. So we have the transmitted wave being faster now because it's in a lower density medium, and there is no phase change. So this is what we do if we just simulate this numerically. In fact, we can write down analytic solutions for how the wavelength and the amplitude of the wave change across the boundary. If we define this is the amplitude, the wavelength is the distance between the peaks, and some initial velocity, then on reflection, the velocity on this side is the same, so v1 just in the opposite direction. We have some reflected wavelengths, some reflected amplitude. On the other side, we have v2, so a different velocity. We have a transmitted amplitude and a transmitted wavelength. The equations for waves at this boundary go like this. The ratio of the reflected amplitude to the incident amplitude is given by this ratio of the velocities. The ratio of the transmitted amplitude to the incident amplitude is given by this ratio of the velocities. For the wavelengths, the reflected wavelength is the same as the incident wavelength because it's not changing medium. It's going from it's not changing strings, it's staying in a string of the same density or changing or staying. For wavelengths, we have that the reflected wavelength is the same as the incident wavelength, which makes sense because it's staying in the same medium. It's staying on the same piece of string with the same linear density, or it's staying in the same gas or whatever it is, depending on the wave. The transmitted wavelength is scaled by the ratio of the velocities. The frequency of the wave is unchanged. So when you go from one medium to another, the velocity changes, the wavelength changes, but the frequency of the wave does not change. So I'll meet these ideas again when we talk about change in refractive index for light waves. It's the same equations for light, obviously, and when light goes from air to glass, it changes velocity, and this tells you how light behaves at an interface. It becomes a little more complicated when we have angles involved as well, because we can have light coming in at and leaving at different angles.